All right, so let's start with part 1, number 9. Okay, so this is unit 3, assignment 3, part 1, number 9. Okay, and here they're asking us to prove an equality. Okay, so it says show that 2 over log base 9 of a, sorry, log base 9 of a minus 1 over 3, sorry, log base 3 of a is equal to 3 over log base 3 of a. Okay, so again, I just want to remind you here that we're trying to show that this thing is equal, so we can't treat it as an equation that we know is already equal. So the idea here is to manipulate one or both sides and show that they're the same. Okay, hoping you're starting to see a pattern here where the first thing I notice about these two sides is that one of the bases is not the same. Okay, so that should almost become an automatic thing that you try to put everything in terms of the same base. And it looks like there's a lot more opportunities for algebraic manipulation on the left-hand side than there is on the right-hand side. So that's why I'm going to choose to start with the left-hand side here. So notice I force myself to write this out separately, okay, so that I don't accidentally start treating this as something that is equal. We're trying to show that it's equal. Okay, so I'm just gonna, look at this one here and say, well, it's at log base 9 and all these other things are in terms of log base 3. Okay, so I'm going to turn everything into log base 3. And the fact that 3 and 9 we know are related makes me feel like this is probably going to be a useful thing to try. So I'm going to start with the left-hand side. So I've got 2 divided by. Notice here I'm going to make this division sign significantly bigger to make sure I know that this fraction in the denominator is indeed in the denominator. So if I apply my change of base formula, it's log base 3 of the original input over log base 3 of the original base. Okay. And here I see 2 things. First of all, I'm dividing a fraction. So that's the same as multiplying the reciprocal. So I'm going to write this out differently. And I notice that log base 3 of 9 is something I can actually evaluate. So that was that connection I was seeing between these 2 bases. Okay, so I'm going to write this out maybe with some detail. So remember here, I'm dividing, it's like dividing fractions. So it's like doing 2 over 1 divided by this fraction in the denominator, which is the same as multiplying by the reciprocal. But what is the reciprocal of this? Well, we already established that log base 3 of 9 is equal to 2. And so in the denominator, log base 3 of 8. I still have my 1 over log base 3 of 8. And so now this is an easy multiplication. It's just 4 over log base 3 of 8 minus 1 over log base 3 of 8. And look what we have here now, 2 fractions with the same denominator. So I can just subtract easily 3 over log base 3 of 8, which is exactly my right-hand side. And so that means I've proved that this is correct. Okay, so again, it's just a little play on this change of base formula. Of course, what's important in all of this is making sure that your arithmetic is spot on. You can't be making any little mistakes here. So here we realize that dividing fractions is the same as multiplying by the reciprocal. And so we got to the answer. All right, any questions on that one there? Nope, okay, so let's move on to the next one that we have. So the next we have is on part 1, I've got number 7. So let's take a look at number 7 here. So I'll continue with unit 3, assignment 3, part 1, number 7. Okay. So number 7 says, describe the transformations that take place on the graph of y equals log base 4 of x. So this is my parent function. So that's telling me that we're performing transformations on this function, okay? And that's being transformed to y equals log base 4 of 16x squared. All right. So when I look at this in terms of transformations, I see an issue, okay? Because there's no transformation that relates to taking powers of the variable, whether it's the y or the x. So as it stands, I cannot describe this as a set of transformations, okay? But because I happen to be working with logarithms, and I know logarithms have some nice things when it comes to powers, the logarithms of powers, hopefully I can use the third law of exponents to help me out here. And I actually see two things that I can do. I'd probably say the most direct way of doing it is, yes, I've got this x squared, but I can't apply the ski-slope rule as it is because it's being multiplied by 16. So the first thing I see is that I can split this up as log base 4 of 16 plus log base 4 of x squared. Okay, in other words, use the first law of logarithms. But now when I do that, I know log base 4 of 16, well, that's an easy thing to calculate because what power of 4 is equal to 16? That's just 2. So I notice here I'm adding a 2. So already I can see I've got a vertical translation, it looks like. And here, now that I've got the logarithm of just a power, I can apply the ski-slope rule here. And look what we have. We just have a transformation of log base 4 of x. So here it looks like we've got a vertical stretch by a factor of 2. And we have a vertical translation 2 up. Okay. And this perfectly valid answer. So any questions on what I did here? Okay. So again, what I did is I noticed that I could split this up using the first law of logarithms. And then from there, I could use the ski-slope rule. And now it's clearly a more traditional transformation of this parent function. The other thing I noticed, though, maybe not as obvious, is I could rewrite the inside part of this differently because 16, and the only reason why I would consider doing this is because 16 is a perfect square. So if you think about it, I could also write this as 4x all squared. And now look what I have. I have the logarithm of a power. I can use the ski-slope rule. And now I could see this as another set of transformations. I can see this as still a vertical stretch, by a factor, again, of 2. But now the second transformation would be a horizontal stretch by a factor, let's let me spell that out right, by a factor of, it's actually not going to be an expansion, it's going to be a compression because I'm going to be multiplying that by the opposite operation, not multiplied by 4, but multiplied by 1/4. Okay, and so what we have is that you can transform log base 4 of x in these two different ways and end up with the same result. Okay, and this is not something that's too surprising. This is something that, certainly with quadratics, you can achieve the same end function with different transformations. Okay, but again, I would say this is probably the more straightforward way of looking at it. Here, you had to think of doing this little bit of algebra. Okay, so any questions on this? I forgot who asked this question here. Let me know if there's any questions on that. No, okay, let's move on. So the next one from part 1 is 8a. So let's see what 8a is asking us. So it says use your calculator to find each of the following to 3 decimal places. Okay, so here it's still unit 3, assignment 3, part 1, number 8a. And here we want to approximate. What is it? Log base 19 of 264. Okay. Excuse me. And the assumption here is that we're working with a non-fancy calculator. So in order to do this, you would have to rewrite it in terms of log base 10, because that's what my calculator can calculate. And so this is essentially just applying the change of base formula, changing to base 10. So let's remember what the change of base formula that we used earlier is. It's log of, in this case here, base 10 of the original input, which is 264, divided by the log of the original base, which is 19. Sorry about that. And so now I just take my calculator and I can find that. So it's log of 264 divided by log of 19. Okay, notice my calculator opens up the brackets automatically. If yours doesn't, you might want to add that in. And here it looks like we have 1.894. Okay, so this here, nothing more than that. It's just about using that change of base formula, changing things into base 10. Okay, any questions on that? No, all right. So let's move. What do we have here? I think we have one more on part 1. It's 2D. All right, so this is unit 3, assignment 3, part 1, number 2D. All right, let's see what 2D is asking for. So it is asking us to evaluate each of these. So it's 7 to the log base 7 of 5. Okay, I guess they're written a little funny there because of the typesetting. So writing it nice and big hopefully will help us take a look at this. And here, well, this is one of those questions that there's really not much thinking that you should be doing, because what I notice is I've got this number 5, which is being inputted into function log base 7, and then that output is going to the function 7 to the x. And we should recognize these as being inverses of each other. Okay, and we know that when we apply a function followed immediately by its inverse, the result is just whatever the original input was. And that's it. That's all it is. It's equal to 5. And again, this only works because these are inverses of each other. If this was 7 to the log base 6 of 5, this would not be quite an easy task to solve. Okay, any questions on that? Okay, so the only thing I'll say here is very often we see this in kind of a, we see it in the opposite direction. We tend to see log, say base 7 of 7 to the 5. We tend to see the logarithm of exponential expression. But of course, these two things, even in this context, are still inverses of each other. And so the effect is the same. Remember that, yes, we have that f inverse of f at x is equal to whatever the original input is, but it also works in the other direction. If you apply the inverse first, followed by the original function, you still get the output. Okay, so if there's no questions on this, let's move on. Again, folks, reminder to please stop me if you have questions at any point. So let's move on to part 2. And what we had in part 2 was 11 and 6. Okay, so let's maybe do number 6 here. So this is unit 3, assignment 3, part 2, number 6. And what this says here is it says a radioactive substance decays from 20 grams to 15 grams in 7 hours. Okay, determine the half-life. And the half-life is essentially how long does it take for it to decay by 1/2. Now, because I didn't cover examples like this, where we use an exponent that's more complex than just x or t, whatever the input variable is, I'm going to do this, and for those of you who know to solve it in those other ways, it's going to look more complex, but it means you don't have to know how to deal with those particular scenarios. Okay, so this might look to some people more complex, but it's a way you can solve this problem kind of in the most straightforward way. Okay, so let's recall what our what our exponential model looks like. Okay, our exponential models look something like this: a equals a naught, whatever the initial value, times the base to whatever our variable exponent is. Okay, so if I make t in hours here, and I guess the amount is going to be in grams, because those are what's given. Well, what I have to do is determine a model that allows me to find the half-life. Okay, so what I can do is just use the information that I have. I know that I'm ending with 15 grams. I'm starting with 20 grams, and it takes 7 hours for this to happen. So in this version of the solution, the a value is my variable. Okay, so I can solve for a. So here I've got 15 over 20 equals a to the 7. And now, in order to isolate a, I just have to take the opposite operation of exponent 7. And the opposite operation would just be the 7th root. It's like taking 1 over 7 of both sides. Okay, so a is just the 7th root of 15 over 20. Now I'm going to leave it as 1 over 7 because that's actually easier to input in my calculator, I think, than using, different roots. Okay, I actually find it easier to input it as a fraction. So here, look at that. I don't even bother, simplifying 15 over 20 because I'll let the calculator do that for me. Okay. So now I just do 15 divided by 20 to the exponent of 1 over 7. And we get 0.96. So that means that my model is a equals a naught, 0.96 to the t. And if I want to know the half-life, how long it takes to go from a naught to half of that, now I can just solve this equation. And as we've seen many times before, the a naughts just cancel out, and now I can solve this. So I'll solve it by taking log base 10 of both sides. Now, when I take log base 10 of this side, I know I'm going to be able to apply the ski slope rule. So I'm going to allow myself to skip that step. Okay, and now I can solve for t. And again, let's put this in our calculator now that we have everything in terms of log base 10. Okay, and what do we have? We have log of 1/2 divided by log of 0.96, and that's about 17. Okay, so it looks like our half-life is about 17 hours. Okay, so again, For those of you taking chemistry, you probably would have solved this in a slightly different way, but I'm solving it using the simple possible exponential model. The first part was using the information given to find my model. And then from there, when I was looking for the half-life, whatever the initial value is, I replaced it by half of that. And I was able to solve using my good old logarithmic strategies. Okay, any questions on this? No, okay. So like I said, I know for some of you, you might look at it and say, that looks a little more complex than it needs to be, but it just means I don't have to talk about, you know, the slightly more complex versions of our exponential models. All right, so the next one was part 2, number 11. So let's look at part 2, number 11. So unit 3, assignment 3, part 2, number 11. And this one, you know, looks like a more interesting problem. Okay, so what they say here is they tell us, okay, that log base A of B is equal to 1 over x. Okay, they tell us that this is true, and they tell us that log base B of, what is it, root A is equal to 3x squared. Okay, and they want us to show that x has to be equal to, what is it, 1 over 6. Okay, so here they tell us that these two things are true. So these equations we know are true, so we can use them. We can manipulate them as we want, and presumably in doing that, we'll get to the fact that x is equal to 1 over 6. Okay, so yet again, I notice that the two bases are different. Okay, I also notice that I've got the same variable occurring in each. And I guess here, since I know that I've got this 3x squared here, and I've got a 1 over x, I would really love to have the x in the numerator. So I guess my first thing that I would probably do is just rewrite this by taking the reciprocal of both sides of this equation. Because we know this equation is true, I can do that. So here, take the reciprocal of the right, I have x, and so this gives me 1 over log base A of B. Now, the other thing I would say is it would be really nice if these logarithms were in terms of the same base. So what I'll do is I'm just going to turn this into log base B. Okay, so the denominator, if I apply the change of base formula, so it's log base B of the original input, which is B. Very nice. I know that's equal to 1 over log base B of the original base. Okay, so this is again all looking very nice because I know that's equal to 1. And remember what I'm doing now. It's 1 divided by this fraction. So that's the same as 1 times the reciprocal. Okay, so it's 1 times the reciprocal. So log base B of A, okay, divided by, well, what's log base B of B? There you go, just equal to 1. So that means x is equal to log base B of A. Okay, so not only have we simplified this by getting the x in the numerator, we also now have it in terms of the same base as the other equation. And this is where I also notice that, hey, log base B of square root of A is the same as A to the 1/2. So now let's take this second equation, and instead of writing square root of A, I can write it as A to the 1/2, and look what that allows me to do, to use the ski slope rule. And now look what I can do. This log base B of A is exactly equal to x. And so now I can substitute that into the other equation. So essentially, what I'm solving is a system of equations, except really with only one variable to work with. Okay, but I needed to work through this change of base. So this is 1/2 x is equal to 3x squared. And I just have a nice, easy polynomial equation. So I don't want this fraction hanging around. So I'll multiply both sides by 2. I bring everything to one side. And in this case here, this is very easily factorable. I certainly do not need to use the quadratic formula. And here we have that x is equal to 0, or solve 6x minus 1 equal to 0. It's one of those things I'm just going to do in my head. X is equal to 1/6. So just judging by this polynomial equation, it looks like there's two answers. But of course, anytime we're dealing with something that gets turned into a polynomial equation, I need to go back and make sure these numbers work. And I see here that x can't be equal to 0 because one of the original equations has 1/x. So that one goes, and the only answer left is 1/6, which is exactly what I wanted to show. Okay. So this one here, we did the sort of change of base type question on the first part. This one here, definitely a little more complex. Okay. Any questions on any of these steps here?
Can you explain the reciprocal part?
In this first part here, like what I did here to go from there to there?
Yeah.
Okay, so this is what you want to keep in mind, is this is actually just about fractions. So if I have 1 divided by x over y, okay, essentially this is just a division of fractions. It's like having 1/1 divided by x over y, okay? Or you could write it as 1/1 divided by x over y. And what is our strategy for dividing fractions is this division becomes the multiplication of the reciprocal. Okay, so I'm just applying the rules for dividing fractions. Dividing two fractions is the same as multiplying by the reciprocal of the denominator, or the second fraction. Okay, so that's what I did here. This just becomes 1 times the reciprocal of the denominator. So what's the reciprocal of the denominator? Well, this fraction just gets flipped around. So the log base b of a goes in the numerator, and the log base b of b goes into the denominator, but that's just equal to 1. Okay. Does that help?
Thank you. I got it.
Perfect. Great. Anything else on this question here? This is a nice question. I like this one. Any other questions we have here? No. Okay. So let's take a look here at what we've got next. So did we ever do number 5? Oh, no, we didn't do number 5 on part 1. I just noticed that one there. And then somebody asked for number 6 on part 2. And then there's the one from the textbook. So let's do number 6 since we're already on part 2, and then we'll go back and do number 5 on part 1. Sorry about that. I missed it before. All right, so let's take a look at what's happening here on wait, now I lost track. Sorry, part 2, number 6.
I think we did part 6 on, part 2, number 6. I think we already did that.
Oh, we did that. Actually, you're right. Yeah, so it's number 5, the one that I missed. Okay, so let's go to unit 3, assignment 3. This is part 1, number 5. And let's see what that is asking us for. So part 1, back to part 1. It says the noise of the school cafeteria is recorded at 50 decibels. So the CAF is 50 decibels. All right. And oh, this is okay at different times. So this is at 10 a.m. And then it's 100 decibels at 12 noon. Okay. By what factor does the intensity of the sound increase at lunchtime? Okay. So, like I said, you would be given this equation if you need it, but let's just write it down. We have that our decibel level is given by 10 times log of the intensity of the sound divided by the intensity of that baseline sound that we had talked about. Okay, so this is our formula. And so what we want to do is we want to compare. And, you know, normally you see me put the bigger one. If I know one is going to be bigger, I'll usually put that in the numerator, but also because they're telling us we want to compare this one to the 10 a.m. one. So I'm going to put this as I12 over I10. So the intensity at 12 p.m. divided by the intensity at 10 a.m. Because of the way they ask the question, they say, by what factor does the intensity increase? Okay, so it's not about the difference, it's about the factor. So it means how many times bigger is one compared to the other. So that's why I'm taking the ratio. So this is what we're looking for. So now what we need to do is find the intensity, or at least some kind of expression for the intensity. And so this is where we're going to use our decibel scale equation. So I know that when the decibel level is 50, okay, I can calculate the intensity, and that'll be at, that's the one at 10 a.m. Okay, and so I essentially want to isolate I10. Okay, so I'd like to get a single logarithmic expression. So step number one is to get rid of that 10. I'm going to divide both sides by 10. Okay, now that I have a single logarithmic expression equal to a number, I'm going to write it in exponential form. So base 10 exponent 5 is equal to I10 over I0. And so I10 is 10 to the 5 times I0. Okay, and then I'm going to repeat the exact same thing for the 12 p.m. Intensity. So here I've got 100 equal 10 times log of I12 over I0. Now here I'm just showing the work because, you know, if I'm trying to show that I understand this process, I want to show all the details. You know, if you were working with this constantly, you would certainly be skipping a lot of steps here. Okay, so same as before, 10 to the power of 10 is equal to that input of I12 over I0. And so I12 is 10 to the 10 times I0. And now I can find that ratio, which I was looking at. Okay, so I12 was 10 to the 10 I0. I10 was 10 to the 5 I0. As we've seen before, those I0s just cancel out. And now we have two powers with the same base. So I subtract, so 10 to the 5. So here we can say that the intensity at 12 noon is, and since this is, you know, it's a big number, but it's, you know, reasonable to write out. So 10 to the 5 would be 100,000 times higher than at 10 a.m. Okay, so even though the decibel level is only doubling in terms of the effect on the intensity of the sound, it's 100,000 times more intense than the sound at 10. Okay, so again, what we're seeing here is this ability to use our logarithm properties to help us work with variables that are stuck inside a logarithmic expression. All right, any questions on that one?
I used the other formula in the notes with beta 2 and beta 1.
Yeah.
I got an answer just 2 times before 100,000. So I'm wondering what's wrong with that.
What did you get as an answer?
I got 99,998.
Oh, well, that's very, very close. That's just a rounding error because you probably ended up putting something into your calculator, right?
No, when I was converting from logarithmic to exponential form,
Yeah.
I got 10 to the 5 equals 2, and then I just subtracted.
10 to the 5 equals 2. What do you mean 10 to the 5 equals 2?
Well, that was right before I calculated my final answer.
Okay, why don't you show that to me?
Okay.
If you want, you can send me a picture and I can give you an answer right away, or if you can wait till tomorrow. But in the end, you got like 99,000. You got almost 100,000?
Yeah.
Okay, so that's probably just a rounding error somewhere. So I would say that that's close enough that, it's something that's even like 0.1% of an error. That's not a big deal. But why don't you show me just so we can be sure? Okay, so either send me a picture of what you have or just show me tomorrow. But it's close enough that I'm not worried about that. Okay, anything else from this one? Okay, so now we've got one from the textbook. So this is 348, number 16. Let me try to find that. 348. Number 16. Okay, so here it says an investment pays 8% interest compounded annually. So write the equation that expresses the amount as a function of time. Okay, so here we're looking for the amount. So we know that we're going to have some initial amount, and every year it's going to be multiplied by a certain number that's going to incorporate the original amount plus the 8%, and we know what is going to do that is 1.08, and then say to the t. So here t is in years and our amount is in dollars. Okay, so there's our model. So here in B, they want us to, so I'm probably not going to do all of these, but let's say I'll do the first one in each. So here it says, how long will it take for this investment to double? Okay, so in this case, I don't know what the initial amount, but I know that I want my final amount to be double whatever the initial amount is. And this is where, like we saw earlier, we're going to be able to solve this problem regardless of what the initial amount. So that indicates to us, and I think this is where we can now answer part of D is the reason why doubling time, and we see for tripling time would be the same thing, because I'd just be multiplying the original amount for T. Instead of multiplying by 2, we'd be multiplying it by 3, is that in our equation, we can just divide both sides by A0 and end up with an equation in only one variable. Okay, so this would be the exact same thing for tripling time. It's just this would be 3 times A0, but the same thing would happen. And then from here, this is just solving this equation. So whether I take log base 1.08 of both sides and then do a change of base, but since I know I'm going to want to get an approximation, I'll just take log base 10 of both sides. Okay. And then, of course, here we can use the ski slope rule and solve for the time. So let's approximate that here. So what do we have? We have log of 2 divided by log of 1.08. Okay, so it takes about 9 years. Okay, so that means any investment at 8% interest compounded annually is going to take 9 years to double in value, and you can determine something similar for tripling time. Okay, so let's take a look here. It says determine the percent increase in the value of the account after 5 years. Okay, now this is interesting here because what we have is we have the amount of years, and we want to know the percent increase in value. Okay, so how would we calculate the percent increase? Okay, well, let's say, so I'm going to do a little work on the side just to justify how I can solve this problem. Okay, so let's say I invested $50. Okay, and at the end of the period of investment, I end up with $60. How could I calculate the percent increase? Well, I could take my $60 and divide it by that $50. So my final amount divided by my initial amount. And what do I get here? I get 60 divided by 50 is 1.2. Okay. Well, what does that represent? That represents that my increase in value would be, well, what does 0.2 represent? Because the 1 represents the $50. The 2 would represent an increase of 20%. Okay. So, it's like taking, say, with tax, $100, you actually pay $113 of it. How do I calculate? You can see that here, that if I do 113 divided by 100, I get 1.13, where the 1 represents the initial amount, and then the 0.13 represents the extra amount that are the taxes. So in order to calculate percent interest, okay, the first thing I would want to do is take my new amount divided by my initial amount. Okay. And so now in my equation, I just realized that I'm essentially taking this equation here and just dividing A naught to the other side. And so now this 1.08 is now being calculated. I forgot what it was, 5 years, 5 times. So by rearranging this equation, this is going to represent the percent increase, or it's going to help me get to the percent increase. Okay, so I reasoned out that if I take the final amount divided by the initial amount, that will help me get the percent increase. And so this is something I can get directly from my model. So it is 1.08 divided by, sorry, to the exponent 5, 1.08 exponent 5 is equal to 1.47. Okay. That means that if this represents the original amount, the 0.47 represents the percent increase. So increases by 47% after 5 years. Okay. Now that's not too surprising, because we know that it takes 9 years to double with compound interest. So it makes sense that after 9 years, 47%, you might say, oh, it's about, it's a little more than half. Well, that's because remember, with compound interest, it gets better and better as you go along. Okay. But yet again, why, if we answer part D, why did it not matter what the initial amount was? Because in the end, this allows me to cancel out the A naughts in B, and in C, I'm taking the ratio of the final value with the initial value. That's the only thing that matters in determining percent increase. So in the end, whether this was, sort of 100,000 over 90,000 or 1 million over 900 million, whatever the numbers would be, it doesn't depend on what the initial amount is. So I guess for D, we could see that the equations needed do not depend on the initial amounts. Oops. Okay, so in part B, it's because the A naughts cancel out. And in C, what happens? You are considering the ratio. Ratio of A, the final amount, to the initial amount. Okay, any questions on this? Now, aside from the math of it, this is something that's important to know, that when you're looking at something like an investment, okay, when you're looking at percentage increases, when you're looking at increases by a particular factor, so in this case here, you know, this doubling or tripling, or here by a particular percentage, it does not depend on the initial amount. The only thing that matters is the actual interest rate that you're working with. Okay, any questions on this? Okay, any other questions that we want to ask? We got a little bit more time, so last call for any other questions. Okay, so if that's it, we will shut it down for now.